Okay, try and some more code. I'm sure you love code lectures. Anyway, so we're going to have a little look at objects in Python and how they're implemented in Python as an example of a practical example of object implementation. And there's a practical, which I hope you'll do this afternoon, on Python objects, where you'll effectively do some of the stuff that I showed there. It's formative, so if you're more concerned in getting your assignment finished and everything, that's your decision, but there is this object practical. So Python. Python is a popular, easy to learn, powerful, dynamic language. I expect, has anybody not heard of Python? No, everybody's heard of Python. Good. It is probably the #1, what you could call scientific programming language at the moment, as far as I'm concerned. It is used by a lot of for sort of not only sort of academic programs, but writing quick scripts. It's very good for writing quick scripts. You can write you can do web development in it, and you can indeed write full-scale programs in Python as well. One of its things is it's multi-platform. So you write Python code on Windows, you can move it to Linux, you can move it to any other platform, Apple, without any problems. From a GIS perspective, it is probably the #1 scripting language for GIS now. Scripting just short programs for doing little jobs. So, for example, ArcGIS has the ArcPy geoprocessing library. It also has a mapping library, and in 10.3.1 there may be new libraries as well. Basically, they're porting a lot of functionality that used to exist only through ArcObjects into Python. So if you want to develop tools and things, you can write in ArcPy. There's lots of open source modules available out there. Modules is just the Python word for libraries, a collection of objects, a collection of programs, a collection of functions. So one of them is GDAL-OGR, which I think I've mentioned. That's for reading, and particularly reading and writing vector and raster data sets, but it also does vector processing and raster processing analysis. Shapely, a slightly higher level language, particularly for vector processing. QGIS has a library called PyQGIS for scripting in QGIS. Same with GRASS. So there are lots and lots of GIS programs that do Python. Now I haven't stuck it up, but if you're interested, I have a whole set of practicals available on particularly open source programming with GDAL-OGR. So if you're interested in doing a bit of Python in your spare time, because I know you've got lots of spare time in your lives, then I can provide those for you. But obviously that's just if you're interested. Also, if you're interested more in ArcPy and ArcGIS, don't forget you've got access to all the Esri online courses for free. So they're very good generally. So if you want to learn a bit of ArcPy, then that might be a good place to do. I suspect you'll do a bit in other programs, certainly in other modules, especially if you're doing the model builder. If you're doing model builder. Python, like all code, is basically written in a text file. The instructions will give you all these details. So you just write it in some kind of text file. This is in Notepad++ that you've seen before. And this is what some Python text looks like. We've got comments with a hash, indicated by the hash character. We import, in this case, a library called random. We create empty lists, and then we write our code. The practical should explain all this. I've never run this practical, with people who haven't already had pre-pro Python. It's part of this the Python course that was previously ran, and I've taken it and I've given it to you as an example of objects. So it'd be interesting to see how you get on with it, if you've had no experience in Python or coding before. We'll discover how well it works. Anyway, you just write this code in a text editor. So the little, this is sort of introducing you to the practical to get an idea what you do in the practical, is we're creating a little program, a set of class, a really basic class hierarchy, number of 3 classes in a class hierarchy. So we're going to define a point object with 3 attributes, x, y, and SRD. SRD being the spatial reference identifier, so a geographic example. We're going to then define a person object that has a name, but also inherits point. So there's an X, Y, and a Z, and an SRD, and a name for person, because they inherit these attributes from point. And then I'm going to create a group object called group, or sorry, an object called group, which has one attribute called group, which is a list of people. And that's a composition relationship. The group has many people, is made up of people, the person inherits these attributes and methods from the point object. So that's what's going to build. There's some methods thrown in as well, of course, not that, but I'm just showing the attributes there. So in Python, and indeed most programming most languages, we define we use the class word. We define a class using the class definition syntax. So we name conventions, always think about conventions. By a convention, classes are given an initial capital in Python. And in these Python objects, properties are variables defined within the class, and methods are functions divided in the class. So we'll see this in a minute. So class point. So here is we define our point object simply as class point, semicolon. Then we define a function. This is how we define a function in Python, called underscore init underscore underscore. Okay, it's a very funny name. What this is and I think I've got a slide actually on this next. This function is what runs when you create a new instance of the class point. So every time you say make a new point, this initiation, because that's what it means, initiation method runs, or function. It's a function in a class. So I may be calling it a function, I may be calling it a method, but as I said, methods are implemented in Python objects as a function embedded within the class definition. We pass in a number of things. We pass in this case, something called self, which means the instance that I am. So you've created a new instance of point. Self means the point that you just created, this point, me. We can pass in an X and a Y and an SRD. And in this case, we've set a default to 4326, which is the WGS84. Doesn't really matter. And then we have a couple of lines of text. Self.x, which is the X value of the instance of the object that we've just created, is set to X. The value of the Y attribute of the object that's been, the instance is set to the Y, and the value of the SRD should be set to the SRD, but seems to have lost the code there. Oh yeah, there we go. I thought I had a slide. The init method is called whenever a new object is created. Self is always the first argument. So every init function always has self there. And self is the object instance itself. So let's see an example. So here's some code using that point definition. So I want to create a new point called point1. I just go point and put in the input coordinates, the variables, the arguments that I want to pass into my point creation. So I've created one point called point1 and one called point2. The first one doesn't have a SRD defined. The second one does have an SRD defined. And there we are. Here I can just do point.x, and that returns me the x attribute of my point, first point. Point.srd, point2.srd returns me the SRD of the second object. Very simple. So that's how you create the basics. Okay, I'm giving you this code in absence of the other code that's around it, but you'll learn that as part of the practical. You experience that as part of the practical. Inheritance. Superclasses in Python are defined in a parenthesized list after a class statement. So in this case, we're creating the person point that inherits, sorry, the class person that inherits the attributes and methods of point. So we put the point object in brackets after our definition statement for person. Here is the initiation method for person. We have self, always have self. We pass in the name argument, the name of the person, and we also pass in another argument here called point, which is a point object, because you're going to pass in a point object that's going to be part of the person object. Again, here we are, self.name, we set in the initiation function, we set the name of the person to the name that we pass in, and we create a shape attribute, an attribute called shape, to be equal to the point object we pass in. There is no control in Python whatsoever as part of this definition that makes the user put in a point object. They could pass into this code any kind of object in Python they liked, any kind of variable they liked, and it would still be assigned to the self.shape. I'm just pointing that out. Python has a very loose implementation of the object paradigm, the object model. It's not a strong, like Java. As I said, in Java, everything has to be objects in Java. Java is a very strong implementation of the object model. Other implementations, such as Python, tend to be a lot looser, and you can do things in Python that the strict object model, theoretical model says you shouldn't be able to do. But that's life. Okay. So that's our definition. So here, so that's how we create inheritance. That's how we implement inheritance. As I said, you can change. There is no controls here in what kind of object you can pass in. We could implement some control here. So in our initiation statement, we could check that x, for example, is a numeric value. We could check that it doesn't exceed the acceptable bounds for, say, WGS84. So check that it doesn't, that the latitude, the y, is between minus 90 and plus 90. We could check that the x is between minus 180 and plus 180. But we'd have to code that as part of the definition here. In objects, the normal way to change the value of an attribute, to get the value of an attribute or set the value attribute, is to define get and set methods. Remember encapsulation. The idea of encapsulation is that you should only have to deal with, you should only be able to interact with your objects through their methods. Okay. This is not the case in Python, but you can, but it's still a good idea to sort of follow the object paradigm and define these get and set methods. This is good practice. So in this case, if I want to get the value of x, okay, I could just create my point object like I did before, point1.x, and I can get the x value. But to follow the object paradigm more closely, I should define these get and set methods. So if I want to get the value of x, I have a method called getX on self that returns the x value of self. If I want to set the x value, I pass in an x value and I set the x value like that. So this is not required in Python, but it's still a good idea because you're following the object approach. Yes?
Can you go back to slide 3?
Yeah.
I know it inherits the point that's in parentheses, but in square brackets, but what's it inheriting? What
Methods and attributes.
So does that mean that you're defining the initiation self-named point, and that self-name and the point bit, does that mean it's in effect putting an X, a Y, and a...
It's adding a point object. So your shape is a composite position relationship with another object called point.
But that point has the same attributes as the point that's inherited.
Yes. If you set, yeah, we'll see it in, I think we'll see it in the example in a minute, yes. So you create a point object, you set its X and its Y and its SRD, then you pass that point object into your initiation method in person, and it gets stored, the point object gets...
If you just leave out the inherit point, would it still work? If you've just got class person...
Yes, it would, because it's a loose implementation of... But it wouldn't know. Well, you could attach the point object there, but then it wouldn't know person, the class person wouldn't know that it should inherit the methods and attributes from point. So it wouldn't know the methods. Hopefully this afternoon, a bit of experience, you'll get the idea. So this is not only inheriting the values of point, but the methods for the point object as well. Okay.
Does that mean it's like linked?
Yes.
Like a foreign key or
something like that. Think of it like that. Hopefully it'll be a bit clearer in a minute. Okay, so we got we done the getting the self method. So here's an example of them. Not a good idea, not strict method. So point 1 equals point with our coordinates. I can use the setX method, point1.setX, and I can set the X value to another value. In this case, it was just a typo error, typed a 3 instead of a 5. And then I can do point.x to get the value, or I could do point.getX to get the value. So we can do either, but this is more objecty or object-oriented code practice than this. This is sloppy code, which Python allows you to do. This is more kind of the stricter object way of doing things. So here's our person method. So here's our class person, with adding a couple more methods in here. So we've got our initiation method, then we've got our get name, set name methods defined to set and get the name of the point object. But here's an example of another method which is providing information on a person. And it just prints out a set of information to the screen about a person object. So you do myperson.info, and it will print out the name of the person is now at the X location of the shape file of the shape attribute in the person, the X value. So we notice we've got self.shape, get the shape attribute, then which is the point object, which we then get the X value from. And then we can do that plus string safe Y plus the SRD. And that will print out information about our person. I am being really brushing over this quite broadly, as you probably appreciate, that the practical will run through this in greater detail. Our third class is a group class, which stores a list of people. And in it, so it stores a list of people, and we're going to implement a method called group.nearestPerson, a nearest person method, which will return the nearest person in our list to a given XY coordinate. And in the example here, I think I actually changed it to make it simpler in the practical. In this example, I used the great circle distances because we're working on WGS84. Everybody knows what a great circle is? Everybody not know what a great circle is? Everyone knows what a great circle is. It's the distance around the planet, basically. It's the shortest distance calculated on the sphere. So I want to calculate the distance on a great circle distance, so on the globe, between a group of people based on a location passing in an XY coordinate in the WGS84 coordinate system. The maths for doing this is pretty complicated, but luckily there's lots of open source code libraries available that allow us to do these kinds of things. So as I say in the example, I think I've just done it on a planar coordinate system just for simplicity. So here's our class group. Define my group, define my initiation, my init method. All we do when we create a group is to create an attribute called group as an empty list. This double square brackets in Python means an empty list. A list is just literally a list of things with a value. So we just create this empty list object in Python, in our group class. Then we can add a method in to add a person. So we've got a person object, we've got a method called addPerson defined on our group, and we do self.group, group being the attribute of our group object, which happens to be called group as well. We can use the append. Append is a method on a list. Yep, method on the list object, and we're adding to our list our person object. So we've created a person object, we add them to our list. Here's the code for removing a person from a list. So we've got a list of people. How do we remove a person? Well, there's a number of different ways we could remove people. In this case, I've removed by name. So what I've got is I'm going to pass in a name, and if I get a match with my name attribute in my group list, then I'm going to delete that person from my list. So I need a little iteration here because I have to loop through all the people in the group. So I start with 0 because that's where you start on an iteration. Iteration just means to repeat. So I do a loop for member in self.group. So I'm just looping through the list. The list is self.group. And each time I get to a person, it's called the member. So if the member name is not equal to the name, it should be equal to the name. That is equal to the name. In Python, to do an equality relationship, you use a double equals sign. So that is if the name in the list is same in the name of the person in the group list matches the name that I passed in, then I pop it, which means remove it on the basis of I being the index in the list. Okay. And then I increment the list. Notice in this example, I don't search through the list until I find a matching name, then delete it, then stop looping. I've looped through all members of the list. And why I've done that is because I might have 2 people in my list with the same name. If I wanted to remove, similarly, I could pass in an index from my list, and I could write a method that removes on the basis of the index, which all the ordering in the list. We can also define things like group information. Here's an example. This is a sort of little method. Sorry about the code going a bit all over the place. So this is providing a list of the people in the group. So info on self, group with, and then it gets the number of people in the group, turns the number of people in the group, and then it lists the name of the person, gets their location in X, gets their location in Y, gets their SID, and just prints out some information on each person in the group. A bit about test code. I think I'll ignore this mostly. This is just an example of using that code, really. We can forget about the if something equals main at the top there. This is about how you run code. Sometimes you want test code to run, sometimes you don't, basically, and this is just a way of doing it. So here's an example. I've created an attribute called group. Perhaps I should have chosen better words, because I've now got a variable called group storing an instance of the class group that has an attribute called group. So yeah, perhaps I should have thought a bit more closely about how I named these things. So I create a new group object called group. I create a point object, and then I create a person object with a name with that point object. I then add the person to my group, I can also create a new person object using a different syntax. Note, I created the point on one line and the person on one line here. Here I'm creating a person all on one line. And I've got the point creation embedded within the person creation. I add the second person. So I've now got a group with 2 people in it. Or I'm going to add my third person. Group info. I can get the information on the person. I didn't actually print out the results from that. And then I can reuse the remove person to get the to remove John Slack. What this is this code would run, and this would output to a window, into a command line window. So when group info is run, you would get the group information printed out. So this, when this time ran, there should be 3 people in the group, and then afterwards we should get 2 people in the group. Ah, there we go. That's what it looks like when you actually run it. So there we go. We've got our various locations. Nearest person. Okay, this is stretching life a little bit, but never mind. So in this case, we're going to calculate this great circle distance. We're going to input a location, point location, and then we're going to get the coordinate for get the nearest person to the coordinate that we pass in. First of all, it's using this library or module called Great Circle that I downloaded off the internet. Just search Great Circle distance Python. 2 seconds later, I have to calculate. I have a module that gives me the result. So this is the in the group. This is the group.nearestPerson method. We're going to pass in an x and a y coordinate. I don't know what's happened. These appear to be not WGS84 coordinates. Never mind. It's the principle that matters. So in this case, we loop through each member in a group. We use the Great Circle module to calculate the distance, Great Circle distance between a particular location and the location of each member. We calculate the distance, and we keep a tab of which one is nearest to the point, which one has the lowest distance to the point. So if the distance of, as we loop through the group list, we keep the minimum distance and the ID of the nearest, of which member of the list has the minimum distance. And then at the end, we can print out which person is closest to. Don't worry about the details of that, as I say, it'll be in the right, okay, that's some test code. So what it ends up with is that we've got a group of 3 members, and then when we run the nearest distance thing, it will kick out text that just tells us that the nearest person, that Susan Meyer is the closest in the group to those coordinates and is 1057.56, very exact, kilometers away from each other. Summary. Okay, that's really, as I say, it's an extremely glossed over version of Python, but you'll get the details in the lecture. So it's a summary. The object model is a very, very powerful data model. I mean, compared with the relational model, I think it is really more intuitive. It's great. It's highly intuitive as a data model. Once you've got your head around how it works, especially from the user perspective, because the user just needs to know what the objects are and what you can do with them. They don't need to know how they operate underneath. But they're just the same as any other program. User beware. The fact that you don't know how they operate inside is both good and bad. It's good that you don't need to know how they operate to use them. It can be bad if you think they work in a particular way, but they in fact work in a slightly different way. So you might well have to, while there's this idea of encapsulation only goes so far. You have to understand what's encapsulated. Even if you don't actually understand the code, you need to understand what it aims to do and what it does. As we've seen, software varies greatly in how strictly the object model is implemented. So in Python, ultimately, if you look inside Python right in its core, everything in Python is an object. But yet, you can program, this is almost like a, it makes my brain hurt, it's like a contradiction in terms. Everything in Python is an object, Yet you don't actually have to do any object programming, particularly in Python, to program in Python. You're using objects, but you don't even need to know that you're using the objects in Python. You just do it. So Python is an example of a sort of loose implementation of the object model. And in particular, the idea of encapsulation is not enforced. We can just do .x on our object, and we can change the attribute in our instance, the attribute value in our instance, without going through a get method. That would be completely unallowed in Java. Java, you would have to go through a method. A method is the only way that you can interact with an object. Indeed, even your most basic program in Java is an object. There is nothing but objects, and you have to use objects all the time in Java. In Python, everything is an object, but you really don't need to know whether they're an object or not to use them. It presently is a bit of a niche database market. As I mentioned earlier, maybe something like 6–7%, it all depends on what figures, of databases out there are object-based databases. Where are these object databases? Well, they tend to be in particularly complex data environments, unsurprisingly, perhaps. Things like, one that I've heard that's quite common is airline booking systems. Seem to be driven mostly object, and one of the early ones in developing objects. As I said, in GIS, I particularly know that my experiences from object databases or object relational databases has been particularly in the utility industry. They use them a lot in the utility industry. Financial markets, I understand, are driven mostly by object systems as well, financial systems. So it tends to be large, complex data situations that you use, that the object model might be used in. So it's a bit of a niche database market. And frankly, it's not got the traction to overtake. In theory, in the 1980s, early 90s, people were saying, well, the relational model is dead. It's the old method, it's history. The reality is that the object model has never eclipsed the relational model, despite its simplicity. One of the problems is lack of standardization. Standardization across the object model has been very low compared with standardization across the relational model. There's also just the huge inertia built into existing systems. If you've got a relational solution, you've got staff, you've got a large pool of staff, trained staff who can use the relational system, and the relational system does the job. Why bother with an object system? Why bother moving across? Why bother translating everything? So there's an element of simply inertia, but there's also an element of, it's only really needed in particularly complex environments.